Okay, the big ones from lesson 4 were the ratio test. We had the geometric test already, the ratio test, the nth term test. But there were a couple times where these were inconclusive. So the nth term test for all right, the nth term test was inconclusive. If L equaled 0. The ratio test, that was inconclusive when? Yes. Okay. So we need some other tests that we could use if we can't come to a conclusion with one of the ones that we already have. So over the course of the next couple days, I'm going to give you a couple each day. So I'm going to give you 3 today, and then a couple more on Monday to finish up chapter 10. So the first one I'm going to give you is something called the integral test. I'll end up putting like a box around this to kind of put it all together. All right, if the function is continuous, always positive, and always decreasing. So these 3 things have to be true in order to apply the integral test. Then, ... So assuming you've already tried the geometric test, you've already tried the nth term test, you've already tried the ratio test, right? Then you notice, okay, all right, I need something else. So my function is continuous. That first of all has to check the checkbox. It's positive always. In other words, there's no negative terms. And it's always decreasing. Okay. Then the series will have the same convergence behavior as the integral. So then switch, abandon the series, find the integral instead, and figure out what if that one converges or diverges. And then the other one the series would behave the same. So if the integral converges, the series will converge. If the integral diverges, the series will diverge. So that is called the integral test. But again, it only applies in certain situations, and hopefully your function is one that you can do the integral of. So let's try a couple. Well, negative e to the x wouldn't work because that's not a positive. E to the negative x would be great because it's continuous. It's still always positive, and it's decreasing. It has a slope that continues to, the values keep falling. So if you can't prove its convergence or divergence any other way. Okay, so does the following series of 1 over n rad n converge or diverge? Question, or does it diverge? How can you tell? So for our purposes, I'm not going to take the time to go through some of the other tests right now. We're just going to jump right into the integral test. So this one can't start at 0, because what would be the problem with starting at 0? I'd be dividing it by 0. So this one starts at 1, going to infinity. So this function is always positive. because we're plugging in positive numbers, so we're always getting a positive thing. It is continuous. There are no breaks because the domain is greater than 0, and so we're fine. And it is always getting smaller because as I plug n in, the denominator keeps getting, what happens to the denominator if I plug n in? The denominator gets bigger, which means the terms themselves get smaller. Okay, so this satisfies everything for the integral test. And so then we are going to find the integral from 1 to infinity of 1 over x rad x dx, which we learned how to do previously. So we've got to swap out our upper bound. We've got to do a substitution. And so it will take the limit and we'll change the upper bound from infinity to b and then go from b to infinity. And then instead of writing 1 over x rad x, I'm going to write x to the negative 3/2. So now I'm ready to do the integral of this expression. So the limit as b approaches infinity of, okay, so I find the antiderivative of x to the negative 3/2, which will be x to the negative 1/2, multiplied by negative 2, plus c going from 1 to b. So this becomes the limit as b approaches infinity of negative 2 over rad b plus 2 over rad 1. And then when I plug infinity into that, I'll get negative 2 over rad infinity, rad infinity, plus 2, which is 0, plus 2. So the answer is 2. So the integral converges on the value of 2. In other words, the area converges on the value of 2. That does not mean the series will converge on the value of 2. It just means that the series will converge to something. The behavior of this is the same, not necessarily the numerical value. All we have to answer is, does this series converge? And the answer is yes, because its integral converges. Because its interval converges, the series will converge. They will not converge to the same number, but their behavior is the same. Let's try another one. So the same question. Will the series that goes from 1 to infinity of 1 over 3n plus 2, will that converge? Again, don't just abandon ratio test and nth term test. Those are going to be, try those first. But the ratio test ends up to be inconclusive because you get L equals 1 for this one. All right, so we're going to assume that we've tried that. And the ratio test for this one, you're going to get L equals 1. So we need the integral test instead. So we'll set up an integral from 1 to infinity of 1 over 3x plus 2 dx. So again, swap out your bound. So the upper bound will be b as the limit of b approaches infinity over 1 over 3x plus 2 dx. So this has a very nice antiderivative of the natural log. So this will become the limit as b approaches infinity of the natural log of the absolute value of 3x plus 2 divided by the chain rule of 3 plus c going from 1 to b. And then I substitute again. So limit of b approaches infinity. I have 1/3 of the natural log of 3b plus 2 minus 1/3 of the natural log of 3 plus 2, which is 1/3 of the natural log of 3 times infinity plus 2 minus 1/3 of the natural log of 5. Now what is 1/3 of the natural log of 3 times infinity plus 2? Still going to be infinity. So I've got infinity minus a constant. And the definition of infinity minus a constant is still infinity, which means the integral diverged. And if the integral diverged, which is the value of the area, that means that the series itself diverges as well. Okay, there, yeah.
So when we did before, that ended up at 2, is that divergent or is that?
The integral converged to 2. In other words, the area is converging to 2. Okay. And so since the area converges to a whole number.
Okay, so for this one only if it's infinity?
Right, infinity means divergent and a constant means convergent. Okay, any questions on that? Okay, that leads us to test number 2. Okay, next test is called the power series test. Or sometimes just abbreviated as P series. Okay, all right. Yeah, that's stats, right? The t-test? Z-test. What's the T series? Oh, okay. All right, so if you are given a series that has a power in the denominator, so that's what a power series is, so 1 over n to any power. If you see a power in the denominator, not a power in the numerator, got to be a power in the denominator. All right, then you have 2 options, then number 1 or number 2. If the power is greater than 1, this should make sense to you. What will happen to the denominator? It's going to get huge. If the denominator gets huge, what happens to the terms? They get small. All right, so if p is greater than 1, the series will converge. If p is greater than or equal to 1, the series will diverge. What did I say? Thank you. Diverges. And again, logically, if p is 1, well then the power is never changing, so the denominator is never changing, but I'm still always adding something and adding something and adding something, and so I won't be able to converge to anything, so just keep adding. And if p is less than 1, that means my denominator is going to get smaller and smaller and smaller, and as the denominator gets smaller, the whole term itself gets bigger and bigger and bigger, so diverging again. Okay, so this is called the P-series test. You can just cite it. You can say, because by the P-series test, since P is 3, it converges. Or by the P-series test, since P is half, you can't prove it, you can't cite this. You would need a different one. Okay. All right, so just a couple quick examples on this one. We could have used this on the one we did originally. N equals 1 to infinity of 1 over n rad n. So the integral test isn't the only test. You could have used the p-series test on this one, because if you express this as 1 over n to the 3/2, since the power, which is 3/2, is greater than 1, that means we have convergence, which we already showed with the integral test. Okay, so that's another way to show it. Yeah, this is a nice that's a popular one. Okay, last one, last test. All right, remember the integral test at the beginning? If f is continuous, always positive, which leads you to think then, well, what do I do if it's not always positive? Okay, all right, so that leads us to another test, which will apply to a certain case. All right, this one's called, the last one for today at least, the alternating series test. Okay, so this one is going to deal with, well, what if the signs switch? Okay, so not always positive. Sometimes they're positive, but sometimes they're negative. And then we'll have another one, which is like, well, what if they're always negative? But we'll deal with that in just a minute. All right, so if we have a series starting at 0 to infinity, which demonstrates that it alternates. Okay, and you guys should remember that -1 to the n plus 1 is going to produce an alternating series. It will be positive, negative, positive, negative, positive, negative, positive, negative. And then all those terms. All right, if we have an alternating series, so number 1. Okay, all terms alternate. All terms decrease. And 3, the limit of the final term is 0. So not another constant. Okay, so the terms have to alternate, the terms have to get smaller, and they have to get smaller in such a way that they approach 0. Not just smaller so that they level off at 2, or smaller so that they level off somewhere else. Smaller all the way until they get to 0. If those 3 things are met, then the series converges. I lost the next page of my notes. Let me find the example. Okay. All right, so something that you might see might be this. All right, so n equals 1 to infinity of -1 to the n, 1 over n squared. So it's sort of like a checkbox thing. Checkbox. Yep, they alternate. I know they're going to alternate because of the -1 to the n. Checkbox number 2. Yep, they decrease. I know they're going to decrease because n squared is just going to continue to grow really large, and so my terms are going to get really small. And they are going to decrease to 0. Because it meets all those things, you would write it nicely, but because it's meeting those things by the alternating series test, this will converge. And an FRQ, if you're lucky, they will say to you, use the ratio test to show the divergence of this series, or use the integral test to show the divergence or convergence of this series. You get really unlucky if they just say, show the convergence or divergence of this series, because then you're like, okay, I got to go through, I got to go through a couple of them until I, so, yeah, you're hoping that they will give you like a push in the right direction. I've seen a multiple choice question, which was like, which of the following tests would be inconclusive for the series? And then they just list, and you got to pick the one that would give you an inconclusive answer, right? So tonight's homework. There are multiple tests that will work for many of these. So I just need you to please identify for me which one you ended up using. If you tried one and didn't work, try a different one so that when we come back on Monday, we can go, yep, I found it to converge because I used this test. And someone else went, I used the nth term test, or oh, I used alternating series, or I used whatever. Okay?